Okay. Just to actually eliminate the background noise, you can mute your mic from your, yeah, thank you. Who else? Here, Daniel, please mute. Mute. Mute are good, mute are good. So let's begin our class. You are welcome, everybody. Welcome to this course. The title of the course is Modern Antenna System Engineering. And it's an extension of
light or electricity.
We are receiving, okay, it's, I think, Kader, is that your, no, it's safe. Okay, so it's an extension of antenna system, which is an undergraduate course. Daniel, it is you. Now it's safe. So please, you make on your audio only. You have some question or maybe comment or something, some feedback. For feedback case, you can use your mic. Unless, please keep it off. Okay, you are welcome to the course of Modern Antenna System Engineering. It's basically an extension of antenna system course, which is given in undergraduate level. Now, in this course, we try to explore different type of antenna technologies, which has wide application in modern era of wireless communication technology. And by the end of the course, you are expected to have the skill, the knowledge of modern antenna systems, which can be used in different wireless communication scenarios. For example, for cellular systems, that means antennas which are used for cellular systems might not be used for like sensor, wireless sensor network, you see. The antenna type probably which is used, which are used for like aircraft, ship, and the like, missile, might not be used for cellular network base station antenna, yeah, for base station. So depending on the application area, basically we may choose different type of antenna which can satisfy the requirement of that specific technology or scenario. So all in all, when you talk about antenna, we are dealing with a system which can create a link between two nodes, that means the transmitter and receiver, without using wire or cable. So basically, antenna uses the air as a medium. So for that reason, wireless communication gate is named from the presence of this radiating or receiving element antenna system. So an antenna is nothing but it's an electrical, it's a device which converts an electrical signal into wave. So basically this electrical signal can be transmitted from the source to the destination using either transmission line or this radiating element antenna. Through the transmission line, normally the intention or the objective of this technology is so as to confine the electrical signal within the medium. You see, by confining the energy, that means the electromagnetic wave, within the transmission medium, it is possible to transmit a signal from the source to the destination. Basically, there are different types of transmission medium or transmission lines. They are actually the coaxial cable, the parallel wire line, and the waveguides can be taken as a good example of transmission line. Whereas the other means of transmitting signal from one source to the from the source to the destination is using antenna, which uses the air or the empty space as a medium to transmit this signal. So the basic intention or objective of an antenna system is so as to radiate the signal which comes from the transmission medium to radiate to the free space. That means the more radiated it is, the more better the radiating element is. That means its main intention is so as to radiate the coming signal to the space. But as far as radiation is concerned, we will come later on. We are much interested on the far field component of the electromagnetic wave. So the main interest of a radiating element is so as to convert the electrical signal to wave. So transmission line and antenna, we can say they have opposite purpose. The main purpose of transmission line is to confine, whereas the main purpose of radiating element, or what you call antenna, is to radiate to the space. So basically, these two transmission medium, actually, they supplement each other. That means the transmission line connect or bring the signal from the system. That means that we can say from the electrical system and feed to the radiating element to the antenna. And the antenna radiates the signal to the space. So actually, we need to have both of them, but their intention is different. So before we proceed to this antenna course, we need to have a working definition. Actually, antenna could be defined as like a transducer, because it converts electrical signal into wave, electromagnetic wave, or it can be considered as yes, I think Jamal, please mute. Okay, so we can have different definition. So before we proceed to the next lesson, let us have a working definition, which is a definition given by connection. Yes. እስኪ የኮኔክሽን ችግር ካለ አሳውቁኝ እኔ የኔ እየተሰማ ካልሆነ probably ብሩክ
እኔ ጋር ችግር የለም
ይሰማል ችግር የለም
all right so let's proceed so we will be following the basic definition or working definition which is given by the IEEE, the International Electrical Electronics Engineers Society, which is a definition which defines this antenna or radiating element as part of a transmitting or receiving system that is designed to radiate or receive electromagnetic wave. So this is basically a working definition for antenna. It is transmitting or receiving. That means this element can act as a transmitter or receiver. So it radiates or receive what? Electromagnetic wave. Let's see the type of antenna. Basically, there are different types of antenna. This antenna type actually come from the structure, how they are built, and basically this antenna can be classified depending on different parameters, antenna parameters that we will be discussing soon. So depending on the physical structure, depending on the electrical characteristics of this radiating element, it is possible to classify radiating element. Basically, let's see the common, or let's use the common way of classifying these radiating elements. That means based on the physical structure. So depending on the physical structure of this radiating element, we can classify an antenna or radiating element as wired antenna or aperture antenna, reflector antenna, so many we will be discussing. Now, to begin with, wired antenna, it's a single element antenna. Basically, this antenna includes the dipole, the monopole, the loop antenna, the helix, you see? And this wire antenna has got wide application. It can be used for personal application. It can be used for automobile application. It can be used for buildings, ships, aircraft, spacecraft, you see? Different this antenna has a wide area of application actually, and this class also contain different variety of wire antennas. We have said that, like the dipole, the monopole, the loop antenna, the helix, they are classified under wire antenna. The other type of classification is the aperture antenna. In this antenna, the horn antennas, the waveguides, is an aperture-like structure, you see? Aperture-like structure.
Sorry.
Yes. Who is speaking? That Jamal? Yes. Okay.
But network is disconnecting from me.
Who are you? Is that
Jamal?
Jamal?
Jamal. Yes.
Okay. I think, Jamal, what you can do is maybe you can mute your video.
video ليه اوكي ايش
You can mute your video. Then maybe you can join
I
us. Yeah?
I mute it
Okay, probably.
and now somewhat it is good now. It's
Yeah.
good now.
Yeah.
Yes.
All right. Now you are watching the rest of us, yeah? Okay. Let's proceed. So,
Okay.
okay. So the aperture antennas is like a horn-like structure. Well, if you remember what a waveguide looks like, it's what you call it an aperture-like structure, you see? So such type of antenna basically can be used in aircraft, spacecraft, because they can be easily flash or mounted to the surface of this so the other variety of or type of antenna is a reflector antenna. Reflector, as the name itself implies, it uses like reflection phenomena. So in this class, the parabolic reflector, the corner reflectors can be classified under this class of antenna. They are very directive. The name itself implies parabolic. Yeah, see, reflector, it reflect, that means it converge using the dish, or what you call it reflector. It collects the impinging electromagnetic wave to a certain focal point. So reflector antennas, it's very popular for its high gain or directivity. And these reflector antennas can be used in radio astronomy, microwave communication, you know, in satellite tracking. So this is other type of antenna category. The other one is lens antenna. Lens antenna, and you know, from the basic characteristics of lens, the lens can be convex or convex. The concave and convex, you see, depending on the combination, you can have a convex plane or convex plane or convex concave plane or concave plane also only. You see, we can use different combination. Actually, the combination results different characteristics. So they are very suitable for high frequency application. It converge or disperse the coming signal. That depending on the combination, normally it results different radiation pattern. The other one is, the other class of antenna is the microstrip antenna. The microstrip, as the name self implies, is micro, and it is strip, you see, metallic strip. It's very small. It is in micro level, you see, and it's made up of metallic-like structure. Basically, it can have like rectangular, circular, or any regular shape. This shape could be printed on the metallic structure, what you call it, the patch. Basically, microstrip antenna contains three elements. The first or the top element is the metallic element. then you get the substrate, then you'll come in the ground plane. You see, depending on the shape of this metallic structure, depending on the height and width of the substrate, depending on the material used to construct the substrate, and depending on the ground plane, normally we can have different type of microstrip antenna which can operate at different operating frequency. Normally, this microstrip antenna has got a wide area of application, like in aircraft, spacecraft, satellites, missiles, cars, mobile phone, and so many applications. Actually, though these microstrip antennas are very small in size, normally they have many limitations, like radiation efficiency, like directivity, like gain. The radiation, if the radiation efficiency is low, it means there exists loss. The voltage standing wave ratio, which means there is huge return loss. So this is somehow, you see, a kind of radiating element which has got some popular application in the current technology, wireless technology. The other type of antenna is array antenna. As the name itself implies, it is array. Array of what? Antenna. You see, by arranging different radiating elements in some fashion, they call it array, it is possible to have a single radiating system. We call it array antenna. The radiating element that constitutes this array antenna can be Yagi, can be microstrip patch, it can be aperture, it can be slotted, it can be waveguide, it can be parabolic. You see, any radiating element can be combined in such way that ultimately the system that we build by arranging in some fashion and feeding by some mechanism, the ultimate goal is to produce very narrow beam. You see, rather than having a radiation pattern which looks like an omnidirectional antenna radiation pattern, the main intention is to have a radiating system which produce very narrow beam, which can be electronically traced to the desired direction. So this radiating element of this system enables us, one, to reduce interference. That means the system will generate only electromagnetic field or power to the direction of the desired user. The rest will be nulled out. That means no radiation will be observed in the direction of the other direction, the unintended direction. The other thing, it helps to extend the range extension. You see, in the conventional system, what we do is to extend the range of, you see, the radiation, what we do is to increase the power. But without, you see, increasing the power using array antenna, it is possible to extend the range. That means it helps to increase the coverage area. The other one is, the other advantage of this array antenna is that it improves the spectral efficiency of the wireless system as a whole. Spectral efficiency. Once the system is directing its beam to the desired direction, it means there is no radiation to the other side. If there is no radiation, it means that area could be used by another another user. So there will be no possibility of interference. That means it enables frequency reuse. This is to show what it looks like. For example, this is for horn antenna. This is for horn antenna. You see, it's a horn-like structure. Horn antenna, different type of horn antenna, as you can see. Different type of horn antenna, circular, rectangular, horn antenna. This one is an aperture antenna, aperture. This is an antenna on aircraft. You see, here we have an antenna for radar, high frequency notch here, fire cable antenna, you see, SATCOM antenna here, very high frequency and ultra high frequency blades, see on the blade. So this aircraft is, equipped with many antenna for different applications. Here, as you can see here, we have antenna, a waveguide-like structure here. So, reflector antenna. An antenna reflector is a device that reflects electromagnetic wave. It reflects an electromagnetic wave that impinges to this physical structure. This reflector can exist as standalone device, just for redirecting RF energy, radio frequency energy, or it can be integrated as part of an antenna, as simply to modify the radiation pattern of the antenna. For example, as we have said, it can be used as, you see, element in building array system, array antenna. So the element can be reflector antenna. It can be, you see, integrated as part of an antenna assembly. The common standalone reflector types are the corner reflector. You place it in some location where you just want to reflect the incoming signal from some direction. And this corner reflector will receive the incoming signal and redirect it to the direction of the intended user. So, such type of antenna is what you call it, corner reflector. See, commonly used in radar. See, corner reflector is used in radar. This is actually very popular application area for corner reflector. The incoming signal will be reflected back. So the other one is we have the flat reflector, which can act as a passive repeater. You see, passive repeater, which do not modify the signal. You see, it's passive repeater. The other common integrated reflector types are parabolic reflector. Actually, this reflector, they have passive and active element. And basically the passive element, always the passive element is longer than the active element. The active element is the one which generates the electrical signal or radiate or convert the electrical signal rather into electromagnetic wave. Whereas the passive element are there to, you see, modify the radiated electromagnetic wave, actually, in terms of direction. For example, to have more directive antenna, like Yagi, you see? This is, you see, reflector antenna. This reflector antenna, as you can see here, this is the passive, and this is active. This is active. This the passive. You see, reflector. It reflects this fire to this the reflector, and the reflector will, you see, modify the radiation pattern of the electromagnetic wave radiated from this system. So this is the feed, whereas this is the reflector. The reflector affects the radiation pattern. The other type of reflector antenna, since we have discussed, is like parabolic reflector, which you all already know. This is a type of, reflector that you might, find in at Sunulta, which you see, which communicate with the satellite. So this big parabolic reflector, which focus beam signal into one point. You see, this is type of reflector that you commonly find, at the top of the roof of every, every home. So there is, in this reflector, there is passive radiator or passive element. Actually, they are metallic element. And they are not electrically connected to any of the system. The only part which is electrically connected in this reflector antenna system is the feed. You see, the feed is electrically connected to the source, whereas the passive radiator or parasitic element are not electrically connected to the radiating element. Rather, after the feed radiate the electromagnetic wave, you see, they are used to alter the behavior of this radiated electromagnetic wave. So they are not electrically connected or attached to the system or the source. So like if you take off the Yagi-Uda antenna, typically it consists of the driven element. Which is connected to the radio receiver or transmitter through the feed line, you see. And the other one is what you call the purpose of the parasitic element is to modify the radiation pattern, as we have said, of the radio wave. More or less, it is to make a directional beam. So the signal which is, or the signal radiated from the feed impine to this parasitic element or passive element, and this element actually alter the nature of the radio wave, and the reflected signal from this parasitic element could be, you see, summed up so as to strengthen to one direction and to cancel out in another direction. That means it's form like superposition. You see, by applying superposition principle, you see some of the signal would sum up to produce more stronger signal to a certain direction, and some of the signal would add up to cancel out, you see, and make null to the unintended direction. In a such way, it form or produce more directive beam, or what you call it, it will exhibit more directive radiation pattern. See, reflector, here you have the driven element, the active element, you see? These all are, you see, director, non-active, and this is a reflector, you see? It is here, driven element, you see, the one which is electrically connected to the system. These are parasitic elements, you see? They are director. And this is, you know, reflector. To reflect, you know, have like electromagnetic radiation to this direction. Electromagnetic radiation to this direction. So maximum gain will be obtained to this direction, to the direction of the multiple director, or opposite to the reflector. This is corner reflector, we have said, corner reflector. Here is the source, you see, the reflector at the back. Here is the source, the reflector at the back. The source here, the reflector. It reflects, you see. So this is the source or the driven element, here, the driven element here. Here we have, you see, driven element. That means you can see here. This is like a parabolic sheet. This is corner, you know, reflector. This is the driven radiator, you see, the driven radiator at the focus of the parabolic. You see, the parabolic sheet results more directivity. That means it reflects the electromagnetic wave to the opposite direction. You see, you can represent like this. In all cases, you can say corner reflector is retroreflector consisting of 3 mutually perpendicular intersecting flat surface, which reflects wave back directly toward the source. You see, here is the source, it reflects back. Here is the source, it reflects back. You see, it reflects back to the source, to that direction. The other type of antenna, lens antenna. Lens antenna is 3-dimensional electromagnetic device which has a reflective index other than unity. It consists of electromagnetic lens along with the feed, and this reflector normally again used to the lens basically used to alter or affect the characteristics of the radiation of this radiating element, the radiation pattern. So basically, whether it is lens antenna or parabolic antenna or corner antenna, there is an active element. We call it the feed. And the other structure are there just to modify the radiation pattern. So lens antenna has the following functions. It generates plane wave from the spherical-like structure. It forms incoming wave front at its focus. That means it helps to focus the incoming electromagnetic wave front. It generates directional electromagnetic radiation, you see. it is used to collimate electromagnetic ray, that means to focus the incoming electromagnetic wave. It controls aperture illumination. These are the main functions of lens antenna. Look at this. Look, we have here the feed point, or rather you better call it focal point. When it is transmitting, it is the feed. When it is receiving, it is the receive. So this is actually the focal point. So here we have the lens. When the electromagnetic wave radiated from this feed impine into this lens, normally this lens helps us to produce a parallel plane wave front directed to some direction. It's more parallel and directional electromagnetic wave will be produced from this lens antenna. While in receiving mode, you see an incoming signal come and impine to this lens structure, and at this time it converges to this focal point. So this is how the lens antenna operates. This is what it looks like, you see. It's more efficient antenna than that of the parabolic, but it is very expensive. Very more secured, not that much exposed for obstruction, but it is expensive. Reflector antenna versus lens antenna. We have here the feed. In both cases, we have the feed. This is for the case of reflector antenna, you see? It comes, see? It generates, produces again a parallel electromagnetic wave when it is acting as a transmitter. Do the reverse when it is acting as receiver. This one is for lens antenna. You see, both of them are very good in producing very narrow beam, focused beam, which is quite comfortable to establish communication between the satellite and the ground station. This is a typical SATCOM antenna. This is the Rexolite. Antenna. Lens antenna. They have the same purpose, but in terms of cost, lens antenna is very costly. This is a picture of microstrip or patch antenna. You see what patch antenna looks like? Look, here is a feed, you see? It come and get connected. This is the patch, you see? This is the patch. This is the patch. That means the microstrip antenna. This is, you see, array of patch antenna. As you can see, many patch antenna are arranged or configured in such way so as to form array element. This is the same thing, you see, it's an array. But what it looks like, the structure of microstrip patch antenna. This is what it looks like. This is a patch. It is patch or microstrip patch. The patch is made up of metallic element. This is a substrate, you see? This is a ground plane. So it's like a type of what? Cavity-like structure, you see? This is a source. This is a ground plane. This is the substrate, which means like dielectrics in capacitor. So here we have the microstrip feed. It feeds the patch, and by some mechanism, it radiates to surrounding. So affecting this structure normally will have or impact on the radiation pattern of this patch antenna. Look, this is array antenna. Array antenna of parabolic element. And this is array antenna of lens antenna. This is array antenna, which is made of microstrip antenna. This is array antenna made of reflector or parabolic structure. This is array antenna made up of microstrip antenna or patch. This is array antenna made up of Yagi. You see, this is what or how we can represent an array antenna. These are the radiating elements. At the back, we have the controller. It controls the signal strength, that means the amplitude. It controls the phase, excitation phase. We have here RF source. We have the power divider. Then using this controller, we can affect the amplitude. Feed supplied to this radiating element, as well as we can control the phase, which is given or which excites this radiating element. You see, in such way we can control at the back. We can control the electrical signal. This will have a direct impact on the radiation pattern of this radiating element. This is what it looks like, the radiation pattern of array antenna. This is radiation pattern of array antenna. Simply just we have assumed a two-dimensional microstrip array antenna. As you can see, this is a small metallic structure. So this is what it looks like. That means the radiation produced from array antenna. This one is what you call it the main beam. These are what you call the side beams. They are not relevant. They are not required. The intention of array antenna is to subsidize or reduce the side lobes and actually produce more strong main beam. See, this is the main beam. This is the side beam. This is due to image. Yeah? Now, we come to antenna parameters. More or less, all antenna or radiating element exhibit or have similar antenna parameters. So as to define or even clearly put the requirement while designing a certain radiating element, normally we need to clearly specify this antenna parameter. You see, antenna parameters. So knowing or understanding what the meaning of these parameters really help us to understand the whole nature of the whole nature of antenna system. Because what type of antenna we design, ultimately the designed antenna will be evaluated based on these antenna parameters. So let's see what these antenna parameters are. Basically, there are different types of antenna parameters, and they are used to express the characteristics of the antenna. Among these, radiation pattern, directivity, gain, polarization, impedance, bandwidth, scanning, and the likes can be taken as the most common antenna parameters. So what do we mean by radiation pattern? When you think of a radiating element, since we are imagining a kind of radiation, you see, so what is that radiation? What it should look like? How we can affect this radiation pattern? You see? So to determine or decide this radiating element, the characteristics of this radiating element is basically fundamental. It's basically required to understand the fundamental definition of what radiation pattern is all about. A radiation pattern, sometimes it's also called antenna pattern, or sometimes it's also called far field pattern, because we are not that much interested in near fields. As far as radiating element is concerned, we are interested in the far field component. You see, the far field component. So radiation pattern can be named as antenna pattern or far field pattern. It's nothing but it is a graphical or mathematical representation of the far field property of an antenna. It's a graphical. It is also possible to express this graphical representation in mathematical form. So it's a graphical or mathematical representation of the far field property of a radiating element. What it looks like. What the radiation looks like at the far field. At some point X, far from the source or the radiator or antenna. It is a spatial distribution of the radiated energy or received energy of the antenna as function of angular variation. Angular variation, when you talk this representation in terms of spherical coordinate system. So it is dependent on the direction, but it's independent of the direction. That means whether it is transmitting or receiving, but it's dependent on the operating frequency. It's very dependent on the operating frequency. So what are the types of antenna pattern? If we have this basic definition for radiation pattern or antenna pattern, what are the common types of antenna patterns? Commonly, we have two antenna pattern. That means the power pattern and the field pattern. For the power pattern, we have the normalized power versus the spherical coordinate position. For the field pattern, we have the normalized E or the magnetic or electric field versus the spherical coordinate position. So since we have said that it's a graphical representation of the electromagnetic wave at the far field, it can be expressed in terms of its power, you see? The power expressed in terms of the spherical coordinate system at the far field, or the electric or magnetic field, the normalized component of the electric and the magnetic field expressed in terms of this spherical coordinate system. We're using this spherical coordinate system. Antenna field types. We have the reactive field, we have the radiation field. The reactive field is the portion of the antenna field characterized by the standing or stationary wave, which represent stored energy. We call it standing wave. We'll discuss it maybe in our next class. Standing wave ratio, stored energy, or loss, or return loss. This is undesired part of radiating element or antenna. The other one is the radiation field, which is what we are interested much or more. It is the portion of the antenna field characterized by radiating or propagating wave, which represented the transmitted signal from the radiating element, the transmitted signal or energy. Okay. Depending on the region, we can also classify antenna field into 3 regions. The reactive near field region, the near field Fresnel region, the far field, the Frown region. The reactive near field region, which is the region immediately surrounding the radiating element, where stored energy or standing wave dominate. The near field region is the region between the reactive near field and the far field, where the radiation field are dominant and the field distribution is dependent on the distance from the radiating element. The far field region, it is the region farthest away from the radiating element, where the field distribution is essentially independent of the distance from the antenna. If we have these 3 regions, that means 3 antenna field regions, how we can, you see, clearly demark these 3 regions. How is that possible? Here is. It is possible to express these 3 regions in terms of the antenna dimension. You see, in terms of the dimension of the radiating element. It is possible to define these 3 regions, that means 3 antenna field region, depending on the size of or the dimension of the radiating element. As you can see, this is the reactive region, this is the near field region, this is the far field region. As you can see here, we have R1, R2. We have D. This is the dimension of the radiating element, that means antenna. We can express R1, that means the region for the near field region, reactive near field region. We can also again demark the radiating near field region, and above R, that means greater than R2, the region is what you call it, the far field region. So you can express this dimension, or you can demark using this R1 and R2 to demark the area if actually this is used to represent for that of omnidirectional or isotropic antenna radiating element. As you can see, R1 0.62 times the root of the dimension of the radiating element. It is squared divided by the wavelengths. Here R2, again 2 times dimension of the radiating element squared divided by the wavelengths. So depending on the antenna pattern, you see, depending on the antenna pattern, that means radiation pattern of the antenna, we can classify antennas or radiator into 3 group or class. This is an isotropic antenna, directional antenna, omnidirectional antenna. An isotropic antenna is nothing but an antenna which radiate electromagnetic wave uniformly in all directions. See, it radiates a uniform electromagnetic radiation in all directions. So this isotropic antenna basically does not exist in a real world, but for theoretical analysis, we use an isotropic antenna as a reference to model our radiating element. You see, to define, to characterize, or it can be used as a benchmark. But the physically existing type of antenna can be classified either under directional or omnidirectional, depending on the radiation pattern or antenna pattern. The directional antenna actually is nothing but it's a type of antenna which exhibits some type of directivity to a certain direction. That means more dominant electromagnetic wave will be radiated to one direction than the other. Whereas when the other type of antenna is the omnidirectional antenna, which is nothing but it's a type of antenna which exhibits uniform electromagnetic radiation in one plane, you see, in one plane. Whereas when we talk of the isotropic antenna or an antenna which exhibits an isotropic pattern, shows a uniform electromagnetic radiation in all directions, you see, but which is not realistic. But the other variety, which is the more popular type of antenna, is omnidirectional antenna, which generate electromagnetic radiation, uniform electromagnetic radiation in a given plane. So the two, that means the directional and omnidirectional antenna are the most popular and physically existing antenna type based on antenna pattern. Antenna pattern definition. By the principal plane pattern, or what you call it, the A plane and H plane pattern of linear polarized antenna. Antenna pattern definition you can define as principal plane pattern, or what you call it, the A plane and H plane. So the A plane, actually it contains the electric field vector. The A plane contains the maximum radiation in this direction. H plane, the plane which contains the magnetic field detector and the direction of maximum radiation of the H plane, the magnetic field. Actually, we can classify in any of the two. That means either E plane or H plane. Electromagnetic, basically, radiation exists in perpendicular. Okay. Antenna pattern parameters. Radiation lobe, the parameter of antenna pattern. We have radiation lobe, the main lobe, the major lobe, the side lobe, the back lobe. See, radiation lobe, a clear peak in the radiation intensity surrounded by region of weaker surrounding intensity. Main lobe, the main beam, the main or the stronger or the maximum radiation. The beam that contain this maximum radiation is what you call it main lobe. Minor lobe, any radiation other than the main lobes, we call it minor lobes. Side lobes, radiation lobes in any direction other than the direction of intended radiation, or we call it main lobe or main beam. The back lobe, the radiation lobe opposite to the main lobe is what we call it back lobe. This is what it looks like. Here we have the main lobe. We have here side lobes. You see, side lobes. These are the side lobes. This is the back lobes, which is opposite to the main lobes. The other antenna parameter is the half power beam width and the first null beam width. Normally, these two are used to characterize the beam width of the main lobe. You see, the main lobe, or we call it major lobe. Actually, they are measured in terms of angle. And the half power beam width is nothing but it's the angular width of the main beam at the half power. Here, half power. If it is normalized, the half, that means at 0.5, it shows the angle. This shows the half power point. So the beam width that we obtain at this half power point is what you call it half power beam width. The other one is the first null beam width. Here, see the first null beam width. Here is the first null. You see, null means becoming zero, no radiation next to the main beam. You see, the first null or zero radiation point next to the main beams are observed at this point. You see, at this point here. So if you draw a line from these two sides, just taking this vertex as, you see, end point, you will draw a tangent line. You see, this is the point where a point where the first null beam width is observed. First null beam width. እንዴት ናችሁ?
አለን
እንዴት ነው? ጥያቄ አለ?
Okay. Yes, it is good.
Do you have any question, suggestion?
Yes, yes, I have.
Okay.
Okay, we have seen types of antenna and also with their application where they are applicable.
Mhm.
While we discussing about the types of antenna, we have seen both reflector antenna and lens antenna have the same purposes, but the lens antenna is the most costly. What about their directivity, their gain, as well as their beam, videos or regarding to those issues?
Okay. Actually, if you observe or look at the basic structure of these two radiating elements, that means the parabolic and lens antenna, more or less one is, half of the other, yeah? Except the feed point. But here, for the lens antenna, just building the dome is going to be expensive. But the level of destruction, you see, and the quality actually is better for that of lens antenna, but still it is possible to have the same type of gain. You see, knowing that this destruction or obstruction are not there, it is possible to have the same characteristics. You see, using the parabolic antenna. The point is, it is more expensive, but in terms of, for example, weather, when it comes to weather, you see, during very rainy season, you see, it's going to affect, bad structure may come and, residual on the surface of the parabolic structure, you see, you need to clean. But when you come to that of the lens, you see, it slide and fall down, you see. For such cases, the lens antenna take, the advantage. But had this all destruction been not there, you see, it is possible to get the same characteristics or radiation pattern or whatever, you see, based on the characterizing parameter of radiating element. It is ideally possible to enjoy the radiation which is generated by a lens antenna using that of parabolic antenna. When you come to that of the physicalization, you see, when it is operating, so the lens antenna brings such, an advantage. But from engineering point of view, it is possible to produce the same, one and the same type of radiation from the two radiating elements. You get my point, Kadir?
Yeah, I got it. But what about the components of from which components they are made make the difference of the costs, or what makes this another case?
No, in terms of the structure, actually there is a lens in between. That is the electromagnetic lens, yeah? It's electromagnetic lens, which is placed in between the dome. You see? So it become another, you see, additional cost to the system. That is why we call it is costly.
Okay.
You see, even from external structure point of view, even building the dome is also another extra cost. Yeah, actually that is what characterizes lens antenna from that of the parabolic antenna. Yeah.
Okay, good. I got the point.
Any question, Brooke? You there? Yes, Brooke. Do you have any question?
No, sir.
Galatach. You're leaving Galatach. Oh. Okay. Jamal. Okay, Daniel, are you there? Daniel, missing. No.
Yes.
Do you have comment or question?
I'm hearing. I have no questions.
How about the quality of the transmission? The quality of the conference, the video and audio quality.
Here I using data, so I muted my video. The audio's quality is good.
All right. Okay. Okay, Ballatach. Yes. Jamal. I think Jamal.
Jamal is out, I think, sir.
Jamal is not there.
Okay. Noi is there. Kapisa, he's living?
Yeah.
Kapisa is living, yeah?
Yeah.
Masfin?
Yes. My question is,
okay.
When we compare to that of parabolic antenna and the Yagi antenna, at this time, much of the time, more of the time, parabolic antenna is coming on use better than the Yagi antenna. What's the reason for this? The people or the one company want to choose parabolic rather than those of Yagi antenna.
Okay, actually it's one based on the operating frequency and the bandwidth. The other one is it's simplicity to mount on a surface. You see, it's not distracted that much, as well as the quality of the signal it receives. You see, the quality of the signal while at in reception mode. You see, in reception mode, the parabolic antenna, you see, collect much signal and actually produce better. For that reason, for example, for this broadcasting, the parabolic antenna shows better than that of the Yagi.
I got it.
Daniel. በለጠች እንዴ ነው እየሰማች አይደለች መሰል በለጠች ሚውት ተደርጓል መሰለኝ እንጂ በለጠች በለጠች አንሚዩት አድርጊው እስኪ አንቺ እንትንሽ ላይ አዎ ሄሎ በለጠች
Yes.
እንዴት ነው ይሰማ ነበር አወዘ ክላሪቲ
ይሰማኛል ነበር
ቪዲዮውም ኦዲዮውም
Yes.
okay good very good Brooke you said it's okay huh? I think Noai you said it's good Daniel he's missing okay So today let's on Wednesday. I hope we are not facing that much problem in terms of video and quality, audio quality, yeah. So we can proceed our lesson, yeah.
Yes.
And
Yes.
if you have any suggestion that could help us to improve, you know, the quality of
Both quality for video as well as for voice is very good, but we are sorry for those leave the for those miss the today's lesson.
Yeah, actually what we can do is maybe I have tried to record it. Yeah, does it show recording at the top of you?
Recording.
Yeah, I'm recording. So what we can do is maybe we can put it on our Telegram group. Yeah, we can share.
Yeah, it's good.
We can share,
Yeah.
and you can maybe those of you who missed the class probably download from the Telegram group and see the presentation. Gabisa. Dear
He's
Gabisa.
not here.
I think he joined us.
He's out now.
Okay. So thank you for our today's lesson. What we are going to do is, you see, we will have a couple of term papers, you see, term papers, and that term papers would be used as means of evaluation. You see, every one of you will make a presentation on your research, so that we'll keep on, you know, proceeding like that. And by the end of the day, the evaluation from these term papers would be used as, you know, final grade. So I kindly request you all to get engaged in the term paper that would be given for you, and try to produce some, you know, quality term paper. Hopefully you'll enjoy our stay in this course, and we'll try to make somehow more research-based lesson than, you know, making some, you know, just making simple presentation or lecturing. We will try to adapt some flavor to that course. And I really appreciate your presence today. And I still insist to stay at home because the pandemic is increasing. So stay safe, stay home. Have a good day. See you on Friday at the same time, yeah?
Yeah, Friday.
Okay, thank you.
Yeah, thank you.
Okay, thank you.
All right, see you.
Okay, bye.